Good afternoon, colleagues. Please, I think before I start, I would like to give one announcement. Colleagues, we have that, today we planned our plenary session, supposed to be start 2 o'clock, now 5 minutes late. From tomorrow, we have the every day, 2 plenary session discussions. Tomorrow morning, 8:30, the first plenary will start. Then the second plenary, afternoon, 2 o'clock. So please try to cooperate to maintain the time. Otherwise, the finishing of the presentations will be delayed. So I would like to request you all, please, everybody in the plenary sessions before 10 minutes before, try to assemble in your seat in the plenary venues. Thank you. Now, I think I'm just introducing the chair of the plenary sessions. I would like to introduce, I think, Professor, this plenary session, I'm not going to talk anything because I'm the part-time panel members. So I would like to introduce Professor Gislason Sigurer. We call Sigi. Sigi is a distinguished professor in geochemistry at the University of Iceland, Institute of Earth Sciences. He earned his PhD in geochemistry from Johns Hopkins University in 1985. Maybe I was very small that time. His research focused on CO2 mineral storage in basic rocks, chemicals and physical erosion rates of basaltic terrains, and the environmental impact of volcanic eruptions. Prof. Gislason co-funded and co-directed to Corvix project from 2006 to 2020, which developed a method to capture of CO2 by dissolving it in water and injecting into the basaltic rocks. His position in geochemistry, including his serving as a president of European Association of Geochemistry. In recognition of his contribution, Prof. Gislason was elected as an international member of American Academy of Arts and Sciences and the National Academy of Sciences in 2024. Prof. Gislason works has significantly advanced the understanding and practical application of carbon sequestrations, contributing to global efforts in combating climate change. Thank you, colleagues. This session is going to handle to Professor Sigi. Thank you.
Thank you very much for the introduction, Vetri. And it's an honor and pleasure to stand here. I'm going to give a 50-minute talk on the climate extremes, the reliance, resilience, and the carbon cycle. But first, basically the proceedings will be such that first the honorary panel here will introduce themselves, and then I give the talk, and then you can pose questions to me on my talk or questions to the panel members. So I would like the panel members to introduce themselves. So if Dominic, if you can start with yourself.
Sure, can. Is it working, the microphone? Good afternoon, everyone. Dominic was furnished my name, Dom Short. I'm German. I got an education by training. I am an environmental and aqueous geochemist. Now at Curtin for the last 15 years, and over 20 years I've been working in the broad field of carbon storage, carbon mineralization, and also hydrogen storage. So that's basically my expertise, and I've been knowing the chair already for over 24 years, actually, when I did postdoc a long time ago in Iceland with him. That's basically our connection. And yeah, so all sorts of studies related to water-rock interaction as they pertain to net carbon emissions and also hydrogen storage.
Thank you, Dom. Good afternoon, everybody. I am Dr. Chidambaram. I am from Kuwait Institute of Scientific Research. They call me Chidam. And I have been working in groundwater chemistry, and my field of expertise is on geochemistry, isotopes, and remote sensing. We have been working on this field since 25 years, and it's good to be associated with you all guys, and hope to have a good discussion. Thank you.
Good afternoon all, I'm Kobus du Plessis. So I'm a local, just close to Cape Town at the University of Stellenbosch, where I'm a professor in civil engineering, in hydrology, and in environmental engineering in the civil engineering department. I'm a former head of the department there. Been there for quite some time, over 20 years, and before that I was in practice for about 17 years. So my main research focus areas are the extremes, looking towards specifically floods and droughts, and then the change in rainfall patterns. Of course, I focus on South Africa specifically, but yes, and I do quite a lot of research with some of the Southern Africa countries regarding regional maximum floods, and pleased to join you here in this discussion. Thanks.
Thank you. I am Cosmo Ngongondo from the University of Malawi, where I serve as a professor in hydrology. And I also have an administrative role as executive dean of the School of Natural and Applied Sciences. And I also serve as a commissioner for the National Commission for Science and Technology. So my research is basically focused on hydrological analysis and modeling. And I use these in the assessments of climate change impacts on various variables of the hydrological cycle. And I also interface with those with a humanities and social sciences background who are researching on intervention. So along the way, I've also had to learn how they do their studies. Thank you very much.
Thank you. My name is Bruno Conicelli. I am a hydrogeologist. I work as a professor at the University of São Paulo in Brazil. I spent the last 15 years working with groundwater recharge related with climate change, using GIS, remote system, and also working with groundwater management. It's a pleasure to be here today. Thank you.
Well, I think we should give them So now we are ready for the talk. And, you know, what I'm going to talk about is the global carbon cycle and some solutions there. And why should we worry about the global carbon cycle? Basically, it's because CO2 or carbon dioxide is actually driving climate change. So the more we know about the carbon cycle, the better. And there is actually a negative feedback within the carbon cycles that actually stabilizes the Earth's climate. And this is not very well known outside of geochemistry. So I would like to bring this up here. Now, all carbon on Earth, the carbon I'm exhaling now as I speak to you, it all comes from rock. And eventually, it will go back to rock. And this picture here that we have here on the screen is from the Eyjafjallajökull eruption. And this is an expression of how we get CO2 from the mantle. Most of what you see here is water vapor, and here's volcanic ash actually that closed the airspace of Europe for 2 weeks. And this one released about 4 million tons per year in a few months. But this is trivial to what we humans do today. But let me take you on a trip through the carbon global cycle, and I will start with how the CO2 gets, into the cycle. Originally, the CO2 comes in here through the oceanic ridges. It comes through the volcanoes here and into the atmosphere. Then it mixes in the atmosphere, and eventually it dissolves in rain. And then CO2 rains on the continents, and that's where CO2 is transformed into bicarbonate. Basically, weathering of calcium, magnesium-rich rocks like basalts transforms these into bicarbonate, and then the bicarbonate, that is this species here, travels to the ocean, where it's then turned into calcium carbonate, and then it's buried as a mineral for millions of years of time. And the trip here from the oceanic ridges, to the continent, takes about 200 million years. So this is the safest way of storing carbon, that is in minerals. Now, how about the organic carbon cycle? You all know this, the photosynthesis, there's where CO2 and water reacts to form, solid, living organism, and oxygen is released, and this is actually what makes our planet habitable. As we respire, as we're doing right now, we turn actually this organic matter that we consumed today for lunch, we consume it back and turn it back into CO2. The only way to preserve this is actually if it's dumped from the continents, and then organic carbon is buried, and it's buried for millions of years in the form of organic carbon, in the form of natural gas, oil, or coal. And then if it is brought up to the surface of the Earth, then oxygen just attacks it again, and CO2 is remitted to the atmosphere. And this is how the carbon cycle works. And let me show you actually how this is actually how the process is. And this is a chemical formula for calcium-rich plagioclase. And plagioclase or feldspars are the most common minerals in the Earth crust. As soon as CO2 and water hits this is anorthite, the calcium-rich one, it's turned into a clay. If you're at high latitude, living at high latitude like me in Iceland, we would form a clay called allophane. Here in South Africa, you would call it probably kaolite, with a little bit of different formula. But what's important here, you release calcium from this, and you release bicarbonate, and you release aqueous silica. So these are dissolved in water, and then it's transported with the rivers to the ocean, where they combine into carbonates with the help of coccoliths, but then eventually fall back to the ocean and form limestone at the bottom of the ocean, or silica that goes into diatoms, and then the diatoms can form actually flints and rocks on the bottom of the ocean. So the overall reaction here is plagioclase, where carbon dioxide goes to clay mineral and to calcite or limestone or chalk, and then the silica is flint. And we can see this, for example, when part of these carbonates are brought up to the ocean, like the cliffs of Dover, the Møns Klint in Denmark and so forth, where you can actually walk the beaches and then you can pick up chalk or flint. Now, there is actually a negative feedback in the system that helps to regulate climate system. The more, let's say, if you have really increased continental drift, you get more CO2 through here, more CO2 through the volcanoes. That, because of the greenhouse effect, that causes temperature to rise. So there is actually a negative feedback in all of this. Let's say that we double the atmospheric concentration, from the Industrial Revolution, from 280 ppm to 560 ppm, and then the strength of the greenhouse effect is about it gives us 3 degrees Celsius raise in temperature. Now, because of the greenhouse effect, temperature will rise, and because hot air can contain more humidity than cold air, that will also mean more precipitation and more runoff from the continents. And because of these reactions for transforming magnesium silicates into carbonate rocks, actually is temperature dependent, that will speed up the dissolution rates of the continents, and it's about 5 or 15% increase. So when I was at Johns Hopkins in the early 80s, we thought that the Earth would kind of just take care of this. You know, the negative feedback would just take care of it and save us from the temperature really rising. And also we thought that at the time there were gigantic experiments done in North Carolina where you had elevated pressure of CO2 in the atmosphere, and you thought that the vegetation in the greenhouses would just take care of it. You would just increase the growth of the vegetation. But of course, it was discovered that you have rate-limiting nutrient that will stop it from happening on a global scale. So basically, is this enough? And the answer is no, because all the silicates on Earth, they fix about 0.5 gigatons of CO2 per year. If we raise it by 40%, if we say because of this maximum response, and we actually measured this in Iceland a couple of decades ago, and then you can bring in extra, you raise it up, but not enough, because anthropogenic emission average from 2014 to 23 is 40 gigatons of CO2 per year. It takes humanity 1 week to emit as much as all the volcanoes, all the ocean ridges, and all the tectonic zones in Iceland emit to the atmosphere. So humanities have really been too good at mining, coals, mining, for fossil fuel, and we are really, really overwhelming the natural carbon cycle. So what's going to happen if we just keep on doing nothing about it, just except we burn more and we burn more and more, and that's shown on this slide here, but I'm looking back in time here. Here we're looking, the scale here is 800,000 years back in time, and this is the concentration is ppm of CO2, and this is in air bubbles in ice on the South Pole, and you can see the concentration here before the Industrial Revolution was 280 ppm. And if you go back here and look at all the data here, and you can see during the glacial time, you have very, very low, about less than 200 ppm concentration, and then at the interstitial, where you had the hot spells during the ice age, then it's about this is about 200, and then this is about 280. Today, or actually last year, the average concentration in the atmosphere was 422. So we have actually increased it from the Industrial Revolution to here about 140 ppm, more than the difference between the interglacial and glacial. So this is a humongous experiment we're doing with this small reservoir of the atmosphere, today. And what this curve shows here, this really terrible curve, and this shows us if we burn all known fossil fuel reserves on Earth, for the past decades, and this was, modeled by Archer, and this made it into the 2 IPCC reports. And if we do nothing about it, we keep on increasing and increasing the rate we burn the fossil fuel, then we go all the way up here in 250 years, and then, most of it is gone, and then we burn all of it in less than 500 years. And the reason why it goes down here is most of the fossil fuel is gone, and then the carbonates in the ocean will dissolve, the corals, and that's kind of an internal system to lower the CO2. They will dissolve, and in the process, they lower the CO2 of the atmosphere, and then the carbonates on land, they will dissolve, and then eventually bring it down to here, and then the silicates take over, but they are much slower than the carbonates, and it would take the silicates not only 100,000 years, about 500,000 years to bring the concentration towards what it was before the Industrial Revolution. And absolutely, we don't want to go there, and we will not go there, because we are reaching now, for the last 10 years, we are reaching a steady state. Well, actually, it looks like we are reaching some kind of a balance at 400 ppm, 400 gigatons of CO2 release. And where has all the CO2 gone? And here is the scale is in gigatons of CO2, and here is 40. And you can see here for the last years, you can see the COVID, down here, and this is 2023, and you can see, in the beginning, it is mainly land use change that caused the increase in carbon in the atmosphere. But after World War II, you have the oil and gas coming in, and here you have the financial crisis, and then COVID down here, and we are up here. But what we can do is we have the technology, because to capture the CO2 that we release, because more than 60% of it is from concentrated source. It is from the smokestack or power plants, industrial and smelters and so forth, and it can be done. And this method of capturing from concentrated source has been known for, the first big experiment was done by the Norwegians in the North Sea in 1996. They've been capturing CO2 there from the gas field using amines, and then they reject it back as a liquid into the underlying sediments, where they store it in sedimentary traps. We don't have had the incentive to do something about it for the last decades, but now this incentive is slowly coming on. And you can see about half of the CO2 has gone in the ocean and on the land, and the half of it what's been emitted resides in the atmosphere. But we have good solutions for doing this, but we're doing it way too slow. This is where we are today, and if we're going to get the 1.5 degree increase compared to the before the Industrial Revolution, we have this time. We have to become carbon neutral before 2040. And we see that we are not heading there. We're not going to make it. And this is more realistic, that we're going here, and we're gonna go for this 2. We're aiming now for 2 or even higher. And if we're gonna go for 2 degrees, we have to be carbon neutral by 2080. And what you see on this diagram this is from an IPCC report in 2018, where they, rather than reporting on the status, they were showing us 4 pathways forward, how we can actually reach our 1.5 degrees Celsius target. And basically, we really, and this is the most wishful thinking, fossil fuel and industry here. This is how we phase out fossil fuel, and we simply phase out fossil fuel before 2050. And even we make, this is agriculture, forestry, and other land use sector in the brown there. And you can see that it even becomes negative, carbon negative. And this is wishful thinking. The other one is much more realistic, and this is actually where we're heading today. If you look at the emission, that came out last year, end of last year, where we're emitting, 41.7 gigatons of CO2. And we will have to, phase out CO2, and we have to capture a lot of CO2 to get to this target. And also, even agriculture, forestry, or the land use sector is actually being, still some of it being, emitting to the atmosphere. And then there's this magic BECCS. This is bioenergy carbon capture. Basically, if we're too slow of capturing from concentrated source, we either have to take the consequences of climate change, or we have to clean up the atmosphere. And in terms of energy and money, that's about 1,000 times more expensive to clean the atmosphere rather than to capture the CO2 from the concentrated source. And that's why I'm really advocating for going straight for the concentrated source. And also, along with that, we play with these other methods of direct CO2 removal from the atmosphere, planting biomass, and even this bioenergy with carbon capture and storage. And I think this one is very promising. because then you grow biomass before it becomes, while it's still positively growing and adding, fixing CO2 before it reaches steady state. Then you cut the biomass, then you burn it, for energy, and then you capture CO2 and you store it for hundreds of years in rocks, and use the energy or heat to other. Also, this can apply for iron smelters and also silicon smelter, to add the carbon to that. And so this is actually how you are moving with. But of course, the time is running out for these solutions. Another big thing now that within the scientific community is very popular, there's a big Nature by Bierling in Nature, earlier this year, on how you can do this on a gigaton scale. But what's happened, you need a humongous landscape. If you're going to get a gigaton, you're going to add about 40 tons of ground basaltic material to the field, per hectare. That's more than what we're fertilizing even in Singapore, per hectare. And you need a land that is equal to the size of India to get up to 1 gigaton of enhanced weathering to clean this up. And then there's direct air capture, and there's the biggest direct air capture plant by Climeworks from Switzerland in Iceland now, where they first started with 4,000 tons, now they scaled it up to 40,000 tons. And it's going to be expensive. The cost of it as it is now is probably $2,000 per ton. It's outrageously expensive, but they're hoping with scale up that they can bring the price down. If we go this way, this industry is going to be similar to the car industry. And this is what's being tried out and fought out as I speak here. So basically, what I will say, we have grossly overwhelmed the natural carbon cycle. And the problem with applying the known techniques, that it has not been used because it costs money and it costs political guts to do it. And also, it takes a long time to win the public on board. And that is really the key for politicians also to do, to help winning the people on board. And thank you very much for your attention. But now, what I would like to, all of you to give me a big applause, big clap, applause. That's the first step. And now I would like to open up the floor after these words, of mine that can be not, can be looked at as not as very possible, positive. But if you have any questions, please, to me or the distinguished panel here, please raise your hand. There's a question down there. Do we have a mic?
Thank you, Prof, for the explanation about the CO2. And it's very clear that geology play a main role of this CO2 part of the cycle in the globe. So my question is very straightforward, because of course the people are worried about the CO2 emission, greenhouse gas, temperature increasing, and so many effects from the CO2. And another side is, of course, the world is also looking for mineral resources. They need mineral resources for their different needs. So how we can balance, if you want to go for exploration of the minerals, they're changing the pattern of the mineral resources. So how it can be affect the CO2 emissions? There is any kind of balancing between the exploration side and also how we can mitigate the CO2 emission.
Yeah, this is a very good question, and a lot of us have thought about it, and feel free to jump in if you have comments. But if I start, you can even combine, mineral mining with carbon capture and storage, especially if you're mining ultramafic rocks or basaltic rocks for mineral like, heavy metals and so forth. You can actually use your pile that you spend some energy in grinding down, and there are several experiments, I didn't discuss it now, that is actually mine tailing, mineralization. And it's promising, but we're talking about something that we need gigatons of solution, but this could contribute to that big pool of mineralization. And this is, there is actually a school friend of mine, and he's started a company in the Northeast and US, and he's really trying to mineralize. And I know there's a group in Australia doing this too, and I don't know if it's being done here in South Africa. I mean, I think with all your mineral tailings, there could be huge possibilities there. Anyone from, okay, please, Dominic.
Pretty much following up on what you just said, in Australia, right, we've got a lot of mining obviously taking place. And now the drive is, with quite a bit of funding, for what we call accelerated mineral carbonation. It is indeed taking the tailings, right, and converting them, converting actually sort of the CO2 that is in the atmosphere into carbonates, all right? And so we have, first, we're trying to also to scavenge metals that are still in the solutions on mine tailings. That is basically your discarded rock, your comminuted rock, into metals, carbonated metals, and also taking the CO2 from the atmosphere. And there's lots of research opportunities happening right now in Australia, especially on the subject, yeah.
Any further comments from the panel? If I can add to that, I mean, there is now, I mean, this is more like academic experiments being done now. People are playing with the idea that injecting very acid solutions, into basaltic rocks and containing CO2, and then you use this acid solution to go for the minerals that you want to bring up to the surface, and some of the precious minerals. And then as the pH gets higher and higher because of the dissolution of the rocks, then you start to mineralize the carbonates. And this is kind of refining what we call the Carfix method, that where we're injecting, soda stream water into the rocks. And so this is one more way of mining. But thank you very much for your excellent questions. More questions, please.
Thank you, Pro.
There's one here up front.
Thanks, Professor, for excellent talk, and it was very rewarding. I have some questions which may be a little bit out of box. So any of the experts can comment upon the industrial CO2 conversion to some chemicals. What is the progress in the respective countries, if you are aware?
Could you repeat the question?
So I'm asking that is there any work progress on industrial CO2 capture and further conversion into chemicals or otherwise?
Well, I mean, this is part of it, the carbon capture, use and storage. So you're talking about the use.
Yes.
Of course, I mean, one of the best ways to store carbon is actually turning it into plastic. We all know that. It's so persistent and it stays forever. But, we have to do this, of course, to get the business part of it. It's always play of money, but the amount is so huge. I mean, if we are, well, I have it in front of me, the last pictures I had during my talk. If we're gonna get to any of our targets, we have to capture at least 20 gigatons or even more to get to our targets. And you can't just produce some, carbonate material out of that. But use is always a big part of it, and it will make it easy to work financially. But carbon capture and storage has to be done on a gigaton scale. Today, and I'm giving a talk right after this in one of the sections here, I'm talking about the technology actually in details. And today, worldwide, we are capturing less than 40 million tons, and most of it is enhanced oil refinery. And so basically we are capturing 0.02% of what we emit today worldwide in carbon capture plants. And this technology has been there since 1996 or even before that. And in Europe now, they have an emission trading scheme that where you actually, the companies that emit more than 100,000 tons per year, they have to buy quota, if they emit. So there all of a sudden now, there's an incentive for industry to do something about it, and it has really made a difference. Now, for example, aluminum smelters in Iceland are contacting us for solutions, and ferrosilicate smelters and so forth, and biofuel, power plants. I mean, they are really concentrated steam, and so basically, the price of the emission trading scheme before the invasion to Ukraine was then in Europe on the market, it was higher than 100 euros per ton. Actually, it was getting to the price, actually, the cost of the technology. So now, everyone in Europe is thinking about it to do this. But the question is, of course, we know the political situation now with Trump in office. It's going to be really, really hard. I mean, you can see the momentum of carbon capture and storage has really slowed down, while the second largest producer today, and actually the largest from the Industrial Revolution, USA, is not being part of the game. So it's really hard to have a momentum for this. So we're probably going to lose about 4 years of momentum loss because of what's happening in the US. Any comments on this? Oh, there's a question, several questions back there.
Thank you very much for a very interesting subject and topic. My name is Melusi Sibanda from University of Zululand, Department of Agriculture. I saw you spoke about reforestation. I just want to check what's the potential for urban agriculture, talking about carbon sequestration, maybe any insights around there?
If I hear you right, you're talking about what's the situation on role of afforestation or reforestation?
Urban agriculture, for instance, in this case.
Basically, I mean, there are places where, and this is one of the reasons why we are reaching kind of like a 40 gigatons kind of plateau, and hopefully it will not keep on going up rather than slowly it will bend down. If we didn't have any regulations anywhere, I'm pretty sure we would have been way much higher. So the regulations they've been put out to curb CO2 emission has worked. And I mean, US until recent, well, US has been declining, and Europe for at least more than a decade now, the total emission. Now, there's a little bit competition for food production with forestry and not forestry. I know in Iceland, for example, we were farmers until just recently, and we overgrazed our land, so there's incredible erosion. So there's huge opportunities there for new forest and grow and store CO2. But the residence time of carbon in forest is from 1 year to 100 years. So we have to, and actually when you grow a tree, you can see actually it's fixing carbon, but then it reaches a steady state. And then eventually, as it declines, it starts to emit some of it, what has been done before. So I think, and this is why people are putting in the backs, and you grow trees or you grow biomass, algae or something, and you burn it before it reaches steady state, while it's still, net fixation, and then you capture it in a concentrated source, and then you take it out of the carbon cycle for hundreds or millions of years. Now, forestry is, will always, there are huge opportunities on Earth, and it will be applied. But forestry cannot save us. We have to play with all kind of different methods to do it. Thank you very much. Or any comments here? Okay. Next question.
Hello. Thank you very much. A very interesting talk. This is such a timely topic. And I would like to follow up with a question about the projections, the 40 gigatons. It sounds this is just the fossil fuel emissions, correct? What I'm saying is how do permafrost releases factor into the equation? Because that's another consequence of the warming Earth. And then on top of that, carbon hydrates, or methane hydrates. Do we have to worry about this part of the equation?
Well, you know it better than me. We have to worry about it. It's a huge source. It's a huge source, and that's part of the. Basically, our aim is to get the CO2 as fast out of the atmosphere as we can, so we prevent some of that happening. You know, the permafrost. I mean, we're even seeing it at high altitude in Iceland. We have permafrost, and it's mainly affecting us. We're getting more and more avalanches as that thaws, you know, down. But of course, if you have something in the Siberian, you know, permafrost, that's scary. And that's another thing too, and it's like a, you know, Russian roulette, you know. So that's definitely something to think about. Good point. Please. You know, you have to jump in, guys. You know, Okay. Next question, please.
So very nice presentation, Professor. So I'm Dr. Selvam from India. So I have two questions. First one is
where is the question? You know.
Here.
Oh, there you are.
So first question is, how does rate of calcium and magnesium silicate weathering affect to the long-term atmospheric CO2 drawdown in the different climate zones? So you're talking about the South African climate zone. So how impact to the different climate can you?
So the question is, how do the calcium and magnesium silicate, you know, react under different climates?
Yes. From the long term of the atmospheric CO2. So how impact to the different climate zones?
I didn't hear the last part, but let me answer first about the weathering rate of calcium and magnesium silicates is very temperature and precipitation dependent.
Yes, that is different climate zone.
Yeah, that covers a different climate zone. So actually, if we have, like, let's say for the Deccan Traps, you know, where we're probably one of the best opportunities in the world to, and I was there in February, you know, for a while, working with people, and there are huge opportunities there because you have humongous amount of basalts, and they have transmissivity down to about 700 meters, you know. So there are lots of possibilities there, but to answer your question more directly, and Dominic is one of the people that has really defined both the temperature and compositional dependence on the weathering of these rocks. And the higher the temperature, the faster the weathering rates and dissolution rates, and the higher the runoff, and we've seen this from natural catchments, then the higher the production of bicarbonates that's going to be flushed out to the ocean. So having reactive rocks in the perfect climate zones, that will help.
Okay.
I can see that you're not happy with my answer. If any of my panel members can help me with it, but because I didn't hear the last part of your question.
Okay.
Thank you. There's a question over here.
Yeah. Thank you very much. I want to come back to forestry, you know, to previous question, and also to address it to our colleague from Brazil. Yeah. There is quite known theory about biotic regulation. It states that only natural ecosystems, not forests, you know, that we grow somewhere in Europe or somewhere else, really natural ecosystems, natural forests, they control the environment, and the environmental parameters which are actually unstable. This temperature, it can go to full glaciation or to full evaporation. We need liquid water and temperature in this range. So the question is, maybe the global community and global climate change community should look into the conservation of natural forests which are still left in Russia. I'm from Russia, in Brazil, also in Africa, in Southern Asia. So those natural resources that are still left in these countries, not in highly developed countries, let's say like Europe or the US. What do you think about it? And I would like to hear the opinion from Brazil as well. Thank you.
Bruno?
Okay. Thank you for your question. It's an important question. Yeah, you are right. We have to preserve forest, the natural forest. In Brazil, we have, of course, the Amazon rainforest, but we have other ecosystems there. And the preservation to these ecosystems is important to keep the hydrological cycle working. For example, I am a hydrogeologist, so from my perspective, we have to save forests, of course, not only to avoid emit new amounts of carbon at the atmosphere, but also to keep the hydrological cycle working. And for that, natural forests are important to increase groundwater recharge, and this recharge keep the soil moisture, and we have the opportunity to increase the amount of water in some watersheds. So it's all interconnected.
Corpus, you want to?
Yeah, just to add on to what my colleague has said on the role of forests. I come from Malawi. So Malawi is a very tiny country in Central Southern Africa, experiencing a lot of environmental degradation. A lot of its forests are gone. Our recent studies have shown that the parts that haven't experienced a considerable deforestation, we have a preservation of the climate signal in terms of the temperatures that are experienced. I can invite you to our recent paper that was published in one of the Springer journals, and we have outlined the challenges that the areas, a good part of 2/3 of Malawi, undergoing considerable environmental degradation, resulting in loss of forest, and this is evident in the climate signal that is emanating from this region. The only part that, instead of experiencing considerable warming, it's experiencing what we call cooling. It's the northern part where most of the forest cover has been preserved, and this is also evident in the nature of the water resources in the northern part of Malawi. Central and southern Malawi, most of the catchment forest is gone. Thank you very much.
Corpus, you want to iterate or take us to the?
I want to stir the pot.
Okay.
Would you like to conclude that first, or can I just go?
Go ahead.
All right. So, one of the things, ladies and gentlemen, that we all, as an engineer, I need to design in the context of climate change. So how do we do this? We've heard quite a number of comments being made early in the preliminary session here about how we experience a lot more frequent flood peaks, for example. The climate change models and how it relates to rainfall doesn't tell a good picture. Not in South Africa at all. We need to be very careful how we design in practice of a signal that's going to take us to 2100 if we design infrastructure for 50 years. What I would like you to be careful about is that I'm working with a lot of local authorities that say, due to climate change, you need to add 15% to your storm rainfall. And my typical question is, why 15%? What about 14%? Of course, it's a trick. They say, well, 40% is not too bad. I said, then why not 10? Or what about 25? Whenever we make decisions regarding the impact of climate change or on extremes, we need to be very careful about that. And what we see specifically in South Africa is too much of something to hide against for very poor management of our infrastructure. So be careful. We know that we are in for trouble, but be careful how you relate it to design. That will end up with significant costs and make it defendable. Now that's a lot easier said than done. Just to stir it a little bit. Thank you.
Thank you very much. Shidam, do you want to control?
Yeah, see, apart from what is being said, it's on climate change actually, and we were initially discussing about carbon. And there are other gases also on greenhouse gases, on nitrous oxides and other methane. At the end of the day, it's about sustainability. So we talk about achieving sustainability on 2030 agendas. I know this part of climate change really is, that they arrange the sustainable developmental goals on a wedding cake structure, and on which they say this climate, life, water, life on land, everything is the base of the entire sustainability. So the climate stirs around all the sustainable developmental goals. So it may be for hunger, for food, for health, for water, and even you have a goal on climate change on sustainable developmental goal 13 is on. So all of this is studied on different scales in different parts of the globe. But the approach is slightly different because the accessibility to information on one country is different in other country. And the information base and the infrastructure, institutional development, it all varies with respect to region. It is not the same throughout the globe. So UN tries to give more concentration on regions where we don't have enough amount of data. So all the models which we develop are based upon the data set which we accumulate upon. And there are still a lot of regions which are still virgin, which do not have enough data. For example, if it is on Kuwait, we have an arid region, and if you go for we cannot go on spot and measure things, it's very hot and it's 54 degrees. So measuring manually will be slightly difficult. We depend on IoT devices, and even IoT devices at extreme temperatures are slightly difficult. Sandstorms are there, and you don't get good signals sometimes. And so we depend upon remote sensing data. And then again, it's on 25 kilometer max what we get. So still we have regions where we don't have enough amount of data, which has to be developed for future. You talk about machine learning, artificial intelligence, or anything of that matter. We need to have data. The base to build upon that is on data. So there are a lot of regions where we need to build upon the data set of climate. And the second thing is on the citizen science, which is very important for addressing any climate change issue. And Europe, they have a citizen science involvement and iChange. There is one Europe initiative on iChange. And similarly, UN has an initiative on links. It's depending upon the local indigenous knowledge system. So that is again incorporating more towards the local climatic variations, which might be we miss as professionals. The local community can support us on providing us the data sets. So UN is concentrating on these links, and then other countries are also on this traditional knowledge of addressing climate changes. So I also feel that citizen science is also very important in playing a very important role in addressing climate change. And that's what I just wanted to steer the pot around on a different direction.
This is very good. We are running out of time now. Anyone else from the panel want to add to this discussion? Or anything now. I mean, this is the end.
Most certainly not on ground water, but I thought I'd like to pick up where Tom left off for the simple reason, and the Chair Sigge was saying it before, when it comes to carbon capture or carbon storage, we are woefully underperforming or behind, not really schedule. And you're absolutely right, Chidam, that we need more data. And we're going to gather that more data, okay? And I'm not the one to say we're running out of data, out of time to gather that data. But what I'm saying is that for the moment, and Ziggy was saying that roughly 40 million tons annually are stored. So we are able to sequester 40 million tons annually. That sounds like a lot, but at the same time, it's 4 gigatons annually that we churn out, okay, through fossil fuel addiction into the atmosphere. That's a factor of 1,000. 3 orders of magnitude are we above of basically underperforming. And although we don't, it's not about entirely sequestering all the emitted CO2, but even if it were only 20%, and some of your climate predictions, they take for granted, even Paris climate, all these agreements, they take for granted that we take out at least 20%. And that would still mean that we are factor 200 underperforming. And that's where I personally get a little bit fidgety or a little bit worried that we're not getting there when it comes about carbon storage. That's what I want to add to the entire discussion. And we haven't even then talked about the hydrological cycle and the effect of climate change on it.
Okay. Thank you. You want to have a...
Yes, as Professor was mentioning about these climate extremes. So that is also an important issue where we'll have to be concentrating on, like recent climatic extremes which are happening in regions where we don't expect, for example, in arid regions like Kuwait, Dubai, and you had a lot of rains recently. And in 2018, you had a very big flood in Kuwait, you know. So that was all on climate extremes, which we didn't expect all these years. And the cycles of increasing these extremes is also differing nowadays. And these, I think, also we'll have to consider about the structures on how we are going to build about. And there were a lot of property loss, there were a lot of damage for life, etc., which was not expected earlier. So our constructions were not sustainable for that climate change structures. So hopefully, I think Professor can add upon that.
Well, we have 1 minute left. Okay.
Done. Okay.
Well, I thank you in the panel. Thank you very much for your contribution. And one final point I would like to make, and I think this is the main problem with climate change and why we're not acting to it. Climate change is a global problem, and CO2 emission is a global problem, but the actions are mainly local. The cost and the pain are local. So this is the crux of the problem. Thank you very much for your attention. We have 10 minutes to make it to the breakaway sessions. So please hurry to the other talks that are starting. Thank you. Oh, yeah. Hey, thank you for your, oops, I'm still on.
Thank you, Professor. Colleagues, I think the one book signed by the minister is missing. If anybody have, please bring it to us. Colleagues, please move to plenary session and parallel session venues. Please. Those who are standing outside, please move to your session. Good afternoon, colleagues. I can see you all tired. That's what no one is come inside. All standing outside, still getting energy. Okay, I think it's a time to start our second session of the day. This session, I think that I would like to introduce the keynote speaker of the session, as well as the chair of the session, the chair and the co-chair of the sessions. Okay. So the first keynote speaker, Professor Vimal Chandra Srivastava, is a distinguished professor in Department of Chemical Engineering at Indian Institute of Technology, Roorkee, India. He previously served as an assistant professor at IIT Varanasi. His research expertise spans chemical and environmental engineering, including alternative fuels, wastewater treatment, and solid waste management, and valorization of spent adsorbents and catalysis. He has authored over 270 peer-reviewed papers from the different publishers and 14 chapters and more than 110 conference publications with over 17,000 citations and H-index of 66. Prof. Srivastava has successfully supervised 22 PhD students and lead more than 10 major sponsored and consultant projects with the combined funding of 60 million. He got on a Young Engineering Award 2012 and Scientist Awards. I think he has a lot of achievements. Due to time constraint, I can restrict it. But finally, I can tell one thing: is affiliated with the several professional bodies, including American Chemical Society, Institution of Engineering, and National Academy of Science. I'm hand over to Prof. Srivastava to continue this session.
Thank you so much, Professor Vetri. Thank you for kind introduction, and thank you for inviting us to be here. And I'm very happy to be here, and I like introduce not only the work that we are doing, also we like to introduce our university as well. So currently I'm a Dean of International Relations, looking forward for international collaborations, research and academic partnership of the institute. Previously I was the chair of the Chemical Engineering Department at IIT Roorkee, and we work a lot on wastewater treatment, industrial pollution abatement, and our group is focusing a lot on industrial pollution abatement. So different types of pollutants getting discharged into the river or into aquatic bodies or into the air. We are looking forward for abatement of such pollution. And in addition, we are working on the CO2 capture and conversion, and a lot of technologies being developed on CO2 to chemicals and CO2 to fuels that our group is doing. So herein we'll be presenting a work on electro-oxidation of pharmaceutical and personal care products. And these different types of pollutants are getting discharged into various aquatic bodies, and they are causing a lot of problems because they are becoming the like part of the food chain with time, and until unless we remove them, so they will be dispersed all across the food chain and they will cause a lot of problems. So before going further, I like to introduce like our institute, IIT Roorkee. Only 2 slides are there. So we are 1847. So we were established in 1847. There is no technical institution in whole of Asia older than us. So it's 1847. Remember, India got independence in 1947. We were established in 100 years just before. Okay, so 1847. And since then we have been doing research, and at those times there was no electrical, chemical, mechanical engineering. It was only 2 types of engineering. One was defense engineering, and another which was not defense was called civil engineering. So the institute had civil engineering, and the first paper which was published from Roorkee was 1861, and it was from our geology department. So at that time only some few departments, geology, earth science and civil engineering, few departments were there, and it was published in 1861. Right now we have 23 departments, 18 centers, 1 schools. Currently we are ranked 339 in the world as per QS ranking. And in the engineering ranking, we are ranked 131 in the world. And the good thing is that IIT Roorkee has very large number of foreign students pursuing PhD or master's degree. And out of those, more than 50% are from Africa. And like our alumni, we have graduated alumni from Ethiopia, maybe 500 plus, from Sudan, from Gambia also, from Zimbabwe and other countries. So there is a lot of presence of Roorkee in African countries with respect to postgraduate degrees and PhDs. And the current also we are going ahead, and we have a lot of collaboration in African countries, and we are looking forward to have greater collaboration in South Africa as well. And this is some of the key points which are there. And more than 105 countries students have actually somehow studied in Roorkee. And currently 300 plus students are there, mostly in PhD and masters. And out of that, around 170 are from African countries. So this is now coming to the topic. Pharmaceutical and personal care products are nowadays being used a lot. In developing countries like India, where the majority of generic medicines are made. So we are a supplier of a lot of generic medicine all over the world. And out of the total production which happens in India, more than 25% of the generic medicine is produced in the state where I belong to, so Uttarakhand. And when these generic medicines and other medicines are produced, we are using them a lot. Nowadays, people are not waiting for the fever to come down. They will use the medicines very quickly. And out of the total medicine which is used by us, most of them is discharged back because we are overusing the medicines. And not only they are causing problems to our body, they are being discharged into the aquatic bodies and where they reside, and they are causing problems like they are becoming part of the food chain, they are getting bioaccumulated, and many times they are bioconcentrated also. And thus the aquatic fishes and other things also get. Similarly, for personal care products, everybody, not only female but male also use a lot of personal care products nowadays. And these personal care products, remember I am a chemical engineer, so I understand all the pharmaceutical care products or personal care products, they have lot of aromatic ring structure. So if you have something aliphatic, it can be broken. If it is the aromatic ring structure, whether it is phenyl, it is some other benzene type of structure or pyridine type of structure, so they are not broken easily. So they cannot be broken by biological means. And also remember, if any of the ring structure contains nitrogenous element, so when they are partially broken, they will form cyanide. So remember, any ring structure which has a nitrogen, now if it is partially broken, it will form a cyanide. So it is possible that the main pollutant may not be as toxic as the secondary intermediate pollutant unless it is fully oxidized. So it's a very challenging and very important to fully oxidize all these pharmaceutical as well as the personal care products during their discharge, after the discharge also. So this is there. They have a lot of potential health risks, already we have explained. So it is very important to degrade them, all these different types of chemicals before they are discharged into the water bodies. Now in India, what it had done is that in 2021 a legislation came under which different types of pharmaceutical products, they have been listed as per that legislation, that before the discharge from any of the industries which are producing them, they have to limit the pollutant up to a certain concentration. So that means all these pharmaceutical industries now need to treat the water before discharging. And that means they have to incorporate new technologies into the existing wastewater treatment systems which exist in these industries. Because the traditional wastewater treatment systems like biological methods cannot actually oxidize these pollutants. So we require advanced oxidation methods for treatment. And now in these various types of advanced oxidation processes, there are a lot of possibilities. So we can use ozone treatment, we can use photo chemical treatment, we can use some other types of remedies where generally what we do is that we produce hydroxyl radicals or some other types of radicals which can react with these pollutants and oxidize them into CO2 and H2O. So this is the general strategy. Now there are certain bottlenecks with respect to the technologies which are being evaluated. Like with the photo oxidation methods, the water has to be transparent, then only light can penetrate, and then only it can oxidize the pharmaceutical pollutants. There could be another strategy that the reactor itself is very thin, and so that the light can penetrate into the water and oxidize the pollutant. So similarly, there are other methods also. I'll not go into the detail, but we study all those methods. There are wet air oxidation methods, there are critical air oxidation methods. So we can use them, but among all these, the electro-oxidation method is very simple, and it can be used for treatment of such wastewaters. So electro-oxidation method incorporates generally the generation of reactive oxygen species and mainly hydroxyl radicals, and these OH radicals actually can react with anybody. Okay, and if they are generated, we use oxidants, we don't want to generate oxidants inside our body. So that's why we use antioxidants. So when we drink alcohols or other types of drinks, so we generate hydroxyl radicals. but we don't want them. So that's why we use antioxidants. But we want hydroxyl radicals to be generated in wastewater because then they can oxidize the pollutants which are present in the wastewater. So we can do this. And these hydroxyl radicals, and there are various types of other reactive oxygen species that can be generated. And they have a very important characteristics that they can oxidize in anything and everything. So this is possible, and certainly depending upon the pH of the wastewater. Now, what happens in the electrochemical method, that we have electrode on which, like in the anode, on the anode we generate OH radical. There are two possibilities of degradation of any pollutant during electrooxidation. One of them is that we have direct oxidation, so under which the pollutant directly goes on the anode surface and gets oxidized. The second thing is that the water goes on the anode surface, we generate hydroxyl radical, and hydroxyl radical reacts with the pollutant and oxidizes them. So this is possible. Now, many a times these PPCPs have a problem that they have nitrogen. And nitrogen is not the simple way of getting carbonaceous compounds oxidized. So if nitrogenous compounds are present, they will form ammonical nitrogen, they can form Geldhal nitrogen, they can form nitrates or nitrites. So we have to use a combination of cathode and anode, because remember nitrogen has 7 valencies. Now it's not a straightforward oxidation. Nitrogen has to be reduced in place of oxidation, because nitrogen we want N2 to be formed. So if nitrate is present, if we oxidize the nitrogen, nitrate will be there. So nitrate we don't want, because nitrate is also dangerous. So we want nitrogen element to be reduced to nitrogen. So we have to play with the combination of anode and cathode in such a manner that nitrogenous compounds get reduced, carbonaceous compounds get oxidized. So we can do that, and I have few patents also on these technologies, because we require a certain amount of play with the reaction chemistries to do that. Certainly we can use lot of novel nanocomposites as electrodes. We are trying to work on, and they require certain characteristics like high conductivity, stability, and very good surface area. And they should have a morphology so that the mass transport of pollutant to the active sites and then discharge of the products from the active sites should be very feasible. So this way we can do that. There is certainly scalability challenges which exist, and we can do that part also. Certainly all the stuff has been done by the research scholars in my group, and they have done a very good characterization of all such studies. I will not go into detail. During this study, I have told that very important when we are doing any pollution degradation, we should check that the intermediate should not be toxic, because in particular if we are using PPCPs, then because most of the pharmaceutical compounds generally contain not only carbonaceous element, they contain nitrogen, they may contain some amount of sulfur also. So intermediates may be more toxic than the parent compound. So we have to perform the toxicity studies and also understand the mechanistic insights of how the degradation is happening. So we can, our group has been doing this, and not only doing the studies, we are trying to model that which type of models like QSR-based models can help predict the toxicity. In fact, we are using machine learning approaches for doing that, and we can predict beforehand, okay, which type of intermediates are going to be formed, and thus we can eliminate those intermediates and try to fully oxidize the material using different approaches. So these studies have been performed by our group. Also, the mechanistic study have been performed. Already I have told there are two main pathways. One is direct, indirect, and also we can check that what are the different intermediates are formed using various types of high characterization studies like HRMS, LCMS, MS, and other techniques. So we can do that. And mechanistic sites also has been identified, and the pathways of degradation have been identified, and not go into the details of such studies. The toxicity assessment has been done using approaches such as QSAR, EcoSR, and all these studies are being performed and are being reported, because if we want to actually use the technique in any pharmaceutical industry, we have to check that all these parameters are met. Also, the cosmetic industry is growing a lot in third world countries, and these actually industries will also come into picture under certain legislation. So all the background chemicals on which different cosmetics are developed, so their degradation studies also need to be done. And if we don't do that, then these, in India, there is one concept of gross polluting industries, and actually time to time now their evaluation is done. And if any of the industry is falling under the red category in the gross polluting industries, so they may be shut down also. So industries are coming forward for doing such studies, and we can do that and thus evaluate whether our technology which we are developing can be used in that particular industry or not. Also, we need to understand the impact assessment, perform impact of the various technologies, and similarly we did for electro-oxidation. During impact assessment, we have to check that how we are able to make the electrodes, how much electricity we are consuming, what is the specific electrical consumption. We perform studies, I'll try to give in a short that we use a lot of mathematical techniques incorporating in our studies, and studies include like multi-objective optimization. That idea is that the pollutant should be fully degraded. That means the COD reduction or the pollutant removal should be maximized. Then second response is the electricity consumption should be minimal. So that means we have one parameter which has to be maximized, but we have another parameter which has to be minimized. And then we want the pH to be neutral. So pH is nominal. So that means we have 3 different parameters, and that makes this a very, very mathematical problem along with the experiment. So that our group we do all these studies, and thus we can optimize the set of parameters which can be used by any industry. And since we are incorporating into the electrical consumption also, so it is always considered well by the industry, because the cost is coming from electricity more often. And also the electrode cost is always higher. So we have to develop such electrodes which can be stable and which can be used for longer time. So these are some of the studies we are doing, and there are certain conclusions, but like key outcomes we have performed all such studies. Electrochemical treatment actually is working well. It cannot be individually be used. It has to be used either a pre-treatment step before biological treatment, or many times after treatment we are able to do. Certainly there are challenges with respect to formation of passive layers, formation of intermediate products which may be more dangerous than the primary pollutant itself. More studies have to be done to incorporate such things, and so that we can take the studies to the industrial level. So there are many key outcomes that we have done, and all these are listed here. And certainly there are future paths to develop low impact, high efficiency electrodes for sustainable PPCP degradation. Integration of real time toxicity monitoring, which is still a challenge. Design of hybrid treatment systems combining electro-oxidation with other AOPs. So we are trying to work on this. Conduct scale-up studies incorporating both LCA and techno-economic aspects for industrial applications. So Roorkee has a lot of pharmaceutical industries nearby, so we are trying to work with them. And similarly, there are other different challenges we are trying to work upon. Roorkee is very close to Himalayas. So if you visit Roorkee and drive from 2 hours, you can actually see this landscape. Okay, so it's the stretch you see is around 400 kilometers of Himalayas, okay, in this photograph. So Roorkee is not very far from there. And since we have a lot of international students on our campus, so diversity and inclusivity is directly incorporated in our campus. And we look forward for hosting many of you in our campus. I'll invite you to visit and please consider it further for your next conference at Roorkee. We are going to host two grand conferences in Roorkee nearby, and some of the friends from here are going to visit, but we will be happy to welcome others also. So we are going to have a Roorkee Water Conclave that is held every 2 years, and that is an annual event. And similarly, one major hydrology-related conference is going to be held this year. Thank you so much. Okay, now I request my co-chair, Dr. Kaveri Sivaraj, to give a talk on a temporal variation of trace elements and microplastics in the core sediments of Encore Creek in North Chennai, Tamil Nadu, India. Thank you.
Thank you, Professor. So thank you, Professor. Good evening. First of all, I would like to thank the convener of this international session. Here, I would like to join with Professor Srivastava for conducting this session. So before going to my presentation, I want to showcase my institute. Since I don't have the slides to show you, I am orally express the glimpse of our university. I am coming from Anna University. It is located in Chennai, southern India, which is the largest technological university in India, affiliating around 400 plus engineering colleges. And we are very strong in engineering graduation courses. And about 26 departments are there, various departments in different campuses. We have engineering, technology, and architectural and basic sciences domains in university. And among the departments, there are 7 science and humanities departments are there. The Department of Geology is one among them. We are very strong in the hydrogeology and environmental geological studies. And we have a very good collaboration with the University of Zululand. I would proudly say that the convener of this program, Professor Vetri, he is the alma mater of Anna University, our department alumni. And he is the very frequent visitors to our university also. Though our department is very strong in the hydrogeology, a small team is also working on the sediment analysis kind of work and a little bit on the micropaleontology. So with that the introduction, I am presenting my PG students' work here to investigate the sediment chemistry as well as the microplastics presence. And in fact, the impact of the geochemistry on the microfossil, that is foraminiferals test that we are trying to investigate during this project. So for this project, we chosen the site. It is not displayed. PPT. Yeah. We chosen that site, that is Ennur Creek, which is located in the northern part of Chennai. It's a very environmentally, it is very important site where there are many industries are situated around that, and different industrial activities invariably the field of the industrial need. There are various industries are located, and also the harbors, around 3 harbors are located, and there is a fisherman's settlement also there in the southern part. And this site is attracted many environmental scientists to investigate the impact on the industrial effects. So we, as a geologist, we are also keen to know what are the changes occurred on the chemistry on the sediments, as well as its impact on the microorganisms, particularly the foraminifera. And also we made an attempt to investigate the different type of microplastics occurrence through depth. So the creek, this receives wastewater from numerous sources. As I pointed, there are different industries around the creek, and there are 2 different rivers are confluencing into the creek, that is Koratlayar and Araniyar. Along the river banks, various industries, they discharge the effluents through the rivers, and it reaches the creek. And as a result, there are environmental threats are found, as the early studies represented about the 40% of the total BOD load measured in the creek environment. And many studies representing a huge concentration of heavy metals are also found in the creek mouth. And this creek environment is severely affected by various natural calamities, as well as the oil spill kind of the accident, environmental threats it is experiencing. To investigate the above set objectives, we had collected a short core sample, and that sample is taken for various investigations like basic sediment analysis, geochemical analysis, microplastic studies, as well as the foraminifera micropaleontological investigations. And we tried to integrate these things. For that investigation, we took a short core at the confluencing point of the 2 river systems. That is Koratlayar in the northern and Araniyar in the southern part, it confluencing. And that environment is having a unique, that is hydrodynamic system during the various high tidal influence times. So we are collected a short core using the PVC pipes and all. And we investigated for the sediment investigations, the down core variation of the sediment materials are distributed, the more coarser materials on the recent sediments, and towards the down core, that is the older sediments that contains finer materials more. And overall, the results that representing more silty and sandy silt type of sediments are found in the sediments. Also, the calcium carbonate and organic carbon, that is organic matter distribution, that represent little variation in the down core distribution of the sediments. The comparative down core variation representing the the elements, elemental concentration, in which the lead, copper, and chromium, they have very much, and also nickel, they have a very much concentration on the down core distribution. And with the geochemical data, we tried to find the pollution factors, contamination factors. So the traditional methods that we followed to evaluate the extent of the pollution, one of the factors is the contamination factor. Then we followed the enrichment factor studies and geoaccumulation index studies also. As per the contamination factors, there are 3 categories where normally we follow to assess the pollution level, that is medium pollution, substantial pollution, and significant high level pollution based on the this calculation we made as per that this given. So in this core sediment, we found there are elements like the chromium, nickel, lead, and cadmium. It shows a significant high-level pollution. That means a high-level concentration that leads the pollution in the studied area. Similarly, the indices of pollution also we evaluated. In that, the contamination factors, what is that minimal enrichment, if it is more than 40 to 60, it is considered as extreme high pollution. In that aspect, it is assessed that the cadmium, nickel, and the whole down core part of the sediments, the lead also, so its richness that is responsible for the extreme high pollution on this site. And the geoaccumulation index, again the 4 to 5 values on the geoaccumulation index, that representing the absence of pollution in extreme high level range. Again the cadmium, that is the one element showing the extreme high level pollution in the studied area. The correlation matrix and the principal component analysis, they normally give the relationship between the various elemental and its association, and based on the factor component analysis, we found there are 3 components, and with this the sources also we try to find from which source the so-called elements might arrive to the specific environment. This study also we attempted. And another study on the same sediments, we were investigated the microplastics. This core yields 4 different type of microplastics, including fibers, fragments, films, and foams, and in which the fibrous type of plastics are found in all the subsamples, whereas fragments and films are minimum in concentration, and foam type of microplastics found only in the recent sediments. It is also found, it shows the variation in down core distribution. The foams are only present on the top core sediments. We also investigated the variation of the colored plastic distribution in the sediments. Among the microplastics, there are about 7 type of colored microplastics are found, in which the white, then followed by the black colored plastics were found abundance. Some of the micro photographs of the microplastics. We made the FTIR investigation for the microplastics, and this study is mainly to find the type of microplastics with the reference of the many, including the Reynolds and so on. There are the polyethylene tetraphthalate, the polyvinyl chloride, and the polythene type of microplastics also we found. The SEM ADAX analysis also we made. We tried to find the elemental concentration of certain plastic materials, and the elemental concentration shows the potassium kind of the element are enriched in all the microplastics, followed by various others. And in the foraminiferal investigations, we mostly found the benthic foraminifera, except the last one, that is the planktonic foraminifera. This creek environment is yielded more the cosmopolitan benthic foraminifera, in which certain forms are abundant in almost all the core samples, in like the ammonia beccarii, and there are certain forms, other forms also. They shown its higher abundance. So among the foraminiferous the population, this ammonia beccarii, that is the one we taken for further studies since its abundance throughout the core samples. We found the various deformities in the core samples. These deformities are due to the environmental stress on its the growing stage. So the foraminifera, as we know, it's a short-living microorganisms. They can survive for very few months maximum. So during the time, is there any environmental stress occurs on its environment, means living conditions, it will adapt. Sometimes it cannot tolerate, so it's reflect its morphological deformity in its test nature. So we found this kind of test deformities like twisted or distorted forms, chambers, the aberrant chamber shape, the reduced size of one or more chambers, prioritized test, and overgrown of the test size, overall test size and all. So this the various deformities are found in some of the forms like nonian ammonia species and Quinqueloclina species and all. These are the microforms, photographs of some of the deformed test. And the foraminiferal test also investigated under the FTIR studies to find the organic matter compound composition present in the test. So this organic component of the microforaminiferal that is giving the direct inference on the variation in the sediment chemistry which is associated with the living environment of the foraminifera. So here we found there are compounds of alkaline, means organic materials like alkalines, the carbonates, amides, carbonyl components, so many. So this test, these are composed of mostly carbonyl components, hydroxyl components, and amide group of components. The most common functional group they are obtaining in the test were carbonyl components ranging from the what is that sorry, the pointer is not there, in that wavelength ranges. So it representing there are macromolecular thermal alteration occurred during the test construction of the short-living organisms. So this given a direct clue on the environmental changes occurred during the formation of the specific fauna. We also had an opportunity to make an attempt that to relate the micro or nanoplastics and its impact on the foraminiferal growth. That can be done in the future studies if you have that culture laboratory conditions. As of now, we don't have that laboratory facilities, so that we are looking for that. Based on the studies, we ensured that certain elements like lead, cadmium, chromium, nickel, and the zinc, they are found to exceed the threshold values recommended by various environmental guidelines. And the spatial distribution pattern that suggests that industrial discharge, port activity, and urban runoff. So we also investigated this study, similar kind of study for surface samples also. With that also we found various findings and all. The environment, the enrichment of heavy metal at the mouth of Cortlia River in the Ennur Craig region is primarily due to industrial effluent and waste discharge, and coupled with the natural sediment transport and deposition process that concentrate these metals in the environment, estuarine environment. And many type of microplastics are found, especially they are more showing its higher concentration on the top samples. Towards the depth, its number of occurrence is very less. that represent the recent industrial activities that yield more plastic waste into the environment. And the micropaleontological studies, it gives the inference on the microbiota that is severely affected by the environmental stress due to the pollution happens in that environment. With this, I conclude that this on my presentation. Thank you.
Thank you, Dr. Kaveri. Now, we'll not take the questions because we started late. Now, I'll invite 4 of the presenters further to join on the stage. And first presenter will be Mr. Francisco Lucas Olembo. If he's here, can you please join on the stage? Yes. So please give a round of applause to all the presenters. So then second, Mr. Oladipo Ulaigundu, if I'm right. Sorry, yes, please, thank you. And we have Dr. Palanicherry, yes, if he's here. Dr. Palanicherry? Okay. Then we have Professor Zian Lee, if he's here. Yeah, please join on the stage. Please join on the stage. Okay. Yes, okay. So we'll begin with the talk by Mr. Francisco Lucas Olembo. His title of presentation is Photocatalytic Performance of Cadmium Dose Zinc Sulfide Nanoparticles for Efficient Degradation of Synthetic Dyes. So, please, thank you.
Good evening, everyone. Yeah, I'm a PhD student at University of Zululand, and at the same time, I am an assistant lecturer from University of Dar es Salaam in Tanzania. So, my supervisors are, as you can see, Dr. Khan and Professor Nerish Levaprasad. Yeah. So, according to my title there, Photocatalytic performance of cadmium-doped zinc sulfide nanoparticles for efficient degradation of synthetic dyes. As we know, I don't know whether you know that 10 to 50% of dyes which are being utilized by our industries, they tend to end up in water bodies. As a result, they tend to affect water sustainability and aquatic life and human health in general. So today we are going to see how we can apply cadmium-doped zinc sulfide for treatment of the dyes. My presentation is going to cover that outlines. As we know that the globally, the increase in industries has led to the use of various dyes in industries. As a result, from 10 to 50%, about 50% of the dyes are being generated as waste, and they end up as industrial effluents to water sources. As we can see, and the effect, And the effect is due to food chain, the effect goes up to the human health. So our concern now is how do we protect water sources, how do we protect aquatic life and human health in general. So various techniques have been used for the degradation or for avoiding the dyes to reach water sources.
One, two.
Thank you. I'm sorry. My eyes I need to see here. So, various techniques have been employed to prevent the dyes from reaching water sources. But as a result, most of them have got some weaknesses. And as we heard from the past presenter, from Prof, he said that at the moment, the advanced oxidation processes are currently favored. Why? Because they don't end up with the waste materials which are dangerous. So they tend to end up with either carbon dioxide and hydrogen or water. So our concern now, we are going to use photocatalytic degradation. But the problem, the materials which are normally used are, they tend to face inferior photocatalytic capacity. So we thought maybe common materials which are used are metal chalcogenides. So we thought maybe we should dope. So in our study, we are going to dope cadmium. We have doped cadmium to zinc sulfide. But still, there are several methods of preparing cadmium-doped zinc sulfide, but most of the method leads to materials which have got poor stability. So we thought we could use solventless hemolysis analysis. I mean solventless hemolysis route, which is low melt. And this is the methodology for preparation of the cadmium-doped zinc sulfide. We used a ligand potassium estylizantate, then we form two different complexes, which are cadmium estylizantate and zinc estylizantate complex. Then we took 30% of cadmium estylizantate and 70% of zinc estylizantate complex, inserted in the furnace, then melt. We didn't use any solvent to get at 250 degrees of centigrade. In 60 minutes or 1 hour, we got cadmium-doped zinc sulfide. Then we had to characterize our material and later on apply for photo degradation. And these are some of the characterization techniques which have been used. The first one there is the TGA, which enables us to make decision on why did we use 250 degrees of centigrade. And we have the term and the HR term, which indicated that as cadmium-doped zinc sulfide has been synthesized, and cadmium is embedded onto zinc sulfide nanomaterials. And we did EDX to identify the composition of our doped material. And the XRD showed that cadmium, the XRD pattern of XRD resembles to that one of zinc sulfide at the inset, but only the width, there's a difference in width. We also did UVVs and PL to get the optical characteristics. So we got that our material tend to absorb at UV. And so during our photocatalysis, we decided to use the UV. It was UV assisted photocatalysis. We didn't use visible, since our material tend to absorb light at the UV area. So we optimized several parameters, including the use of hydrogen peroxide, initial dye concentration, pH, and the amount of adsorbent. So as you can see, we did our material in dark condition in order to ensure that the absorption first, to see how the material, those synthesized catalysts can absorb the dyes. And the dye which we used was methylene blue. And those are the results. It showed, the effectiveness was showed above 80% in both at acidic P condition and neutral condition, and in alkaline condition. Also, by varying hydrogen peroxide amount, we wanted to know the effect of hydrogen peroxide, and we saw that by using in the absence of hydrogen peroxide, by using 0.5 mils of 0.1 more hydrogen peroxide, and also by using 1 mil of 0.5 mole hydrogen peroxide. So both of them showed that they are effective, but the effectiveness tend to differ. The last graph there shows the optimization parameter of the catalyst dosage. So we used that first, the black pattern shows that it was a blank, that is no catalyst. We did it only under UV. But the others, so as we increase the amount of catalyst dose, our photodegradation tend to increase. And here I wanted to see the model, which model does our process degradation follows. And all the reactions, those in hydrogen peroxide, the effect of hydrogen peroxide, the effect of pH, initial dye concentration, and the effect of catalyst dosage, all of them follow pseudo-first order, since the constant R square is observed, you can see it. So we tested the stability and the recyclability or usability of our material, synthesized material. Yeah, and also we wanted to compare the photocatalytic and another method which was sonocatalytic. So both of them showed high performance under several cycles. We went up to 6 cycles and they are still stable. We didn't there, then we decided to compare that was methylene blue, but we wanted to see under the optimized character parameters of which were being used with methylene blue. How will it affect other dyes? So we tested the other dyes. As we can see, the first column from top to down, that is CLR is Congo red. Then we have methylene blue, methyl orange, and rhodamine B. So the second column, which was the methylene blue, we can see that was the optimized parameter was investigated according to it, but later on applied to other dyes. So we can see how other dyes also, most of them, the degradation was achieved somehow. But in other cases like rhodamine B, we need to optimize the parameters according to rhodamine B and also methyl orange. So these are the efficiency, degradation efficiency with using various dyes: Congo red, methyl blue, methyl orange, and rhodamine B. With photocatalytic, and we also compared with sonocatalytic, that is the use of sound waves. So both of them showed high efficient. In conclusion, we were able to synthesize zinc, cadmium-doped zinc sulfide through melt method, and our synthesized materials showed high efficiency in photo and sonocatalytic degradation of dyes. So this study shows that cadmium-doped zinc sulfide can be used as a photocatalytic for dye degradation. Thank you for listening.
So the next presentation on assessment and monitoring of phthalates in wastewater by Mr. Olabido Olangundudu.
Hello everyone, good afternoon. My name is Oladipo Ologududu and I'll be presenting to you a topic titled Assessment and Monitoring of Phthalates in Wastewater, a case study of Toyando Wastewater Treatment Plant. I'm a student at the University of Venda. And, all right. So this is a brief rundown of the background, of the outline of my presentation. So to start with, phthalates are one of the most common emerging contaminants, emerging chemicals we have on Earth today. They are highly used in a lot of industrial processes. You find them in toys, you find them in medical devices, building materials. You find them in even food packaging materials, cosmetics, personal care products. They are almost everywhere. And in the world today, you have a very, very large, production of phthalates, about 11 billion pounds. That's approximately 5 billion kilograms, which is really a lot. So because of that, the environment is almost filled with phthalates. You have a lot of environmental pollution as a result of the prevalence of use of phthalates in our environment today. Unfortunately, they are not covalently bonded to their parent material. So you find a lot of phthalates leaching out into the environmental media. Also, phthalates are endocrine disrupting chemicals, and they are able to interfere with the normal functioning of the hormonal system, like Prof was talking about earlier. These are some of the structures of common phthalates that you find around. They are basically a benzene ring attached to two ester groups, which are subsequently attached to either an alkyl or an aryl group. So you have dibutyl phthalates, you have diethyl phthalates, bis-2-ethylhexyl phthalates, benzyl butyl phthalates. A lot of these have been declared as priority pollutants because they do not exhibit good effects, especially when they get into humans and organisms. So let's continue to our background. The emphasis of this study is more on wastewater treatment plants. And we all know that wastewater treatment plants are one of the last line of defense when it comes to removal or decontamination of toxic materials, in this case, water. Generally, wastewater treatment plants in South Africa have been researched, and we found out that the quality of these effluents have not been really effective, and they end up contaminating the final water bodies, whereby they are released into streams, surface water in general. And many authors have also argued that these wastewater treatment plants are also not effective at decontaminating emerging contaminants. In this case, we are looking at phthalates. So this is a study area. Thohoyandou is located in Thulamela municipality in Venda, Limpopo province. It's a house to approximately 70,000 people, and this is where the wastewater treatment plant is located. So the treatment plant receives basically both domestic and a little of industrial waste, and the effluents are eventually released into surface water. It's almost immediately released into Vudi River, which connects to Luvuvu River, and then eventually into Nandoni Dam. And that dam, you have a lot of domestic or recreational activities, even fishing, going on in that dam. And this wastewater treatment plant was initially designed for small-scale use, but as population of Thohoyandou began to increase, you have that over time, the wastewater treatment plant has been overstressed. Initially, it was designed for 4.6 megaliters per day. As at 2023, it's already given an output of 49, which means that we have an issue in our hands to deal with. So this is a problem statement in a summarized form. Studies have already shown that wastewater treatment plants in South Africa contain phthalates in the effluents and other emerging contaminants. Secondly, like I said, these wastewater treatment plants' effluents are released into surface water that eventually people use for different domestic purposes. So residents rely on this surface water, which are the receiving end of effluents from wastewater treatment plants, for domestic use. They use them in the untreated form. As a matter of fact, I remember some time ago I went to take sampling, and I found people washing vegetables that they would take to the market from this surface water. And then thirdly, we haven't had a study that has actually monitored the levels of phthalates in these wastewater treatment plants. So this is the objective: firstly, to monitor the levels of 4 prominent phthalates. Secondly, is to estimate the removal capacity of this wastewater treatment plant. And then let's find out what the ecological risk impact will look like. So this is the methodology. This is how I went about this research. It's a small part of my research, by the way. So influence and effluents from these wastewater treatment plants was sampled continuously for 6 months, once a month, and then analyzed. So each time the samples were taken, they were stored, of course, at 4 degrees, and then transported to the laboratory where they were analyzed within 48 hours. So the samples were first filtered through glass fiber filters to take away the suspended particulates, and then they were ran through SPE, solid phase extraction, to be able to extract the analytes of interest as we are looking for using SEPAC cartridges from waters. And then the final elution was done with a ratio of methanol and dichloromethane. The final process samples were eventually sent for analysis with LC-MS-MS, where it was quantified. With respect to quality control, these are some of the precautions that were taken when carrying out this experiment. Each of the samples were run in technical duplicates and, of course, also run in triplicates. Each sample was carried out in triplicates. The use of plastics were completely avoided because phthalates are used in plastics, and you wouldn't want to contaminate what we are trying to extract or interfere with the separation processes. Then a standard calibration curve was also used to quantify the analytes. Then blank samples were also run in order to detect any background contamination or memory effect from the liquid chromatography. So this is method validation parameters for this experiment. Just to take you through, for dibutyl phthalates, so DBP is dibutyl phthalates, then DOP is dioctyl phthalates, then DHP is bis-2-ethyl hexylphthalates, and then DEP is diethyl phthalates. And you can see that there's a very, very close similarity between dibutyl and then DEP, 0.28 and 0.29 microgram per liter. And a similarity with those is that they are both low molecular weights phthalates, and then DOP and DHP are high molecular weights. With respect to the percentage recovery, it ranges between 74 to 126, which, according to the USEPA model, states that if your percentage recovery is between 70 to 130%, you're actually fine. And then the correlation is almost 1 for all of them. Yeah, so this is the level of the phthalates over a period of 6 months from September to January, where this study was carried out. For one of them, dibutyl phthalate, you can see that consistently we have more of the phthalates, the contaminants, in the effluents rather than in the influents. We would ordinarily expect the order to be the other way around, but this is what research is saying, that you have more phthalates released for dibutyl phthalates in the effluent than in the effluent. For dioctyl phthalates, it's almost the same thing. You can see that all through the months, except in December, you have in the influents higher than the effluents, but all through you find effluents consistently being higher than the influents. So DHP as well, you also have a similar situation of effluents being higher, except in January, and then diethyl phthalates. Here, this is the only analytes from this group of phthalates that have been examined where you find consistent reduction for 6 months, where the effluent is lower than the influent. All right, so to examine how effective the wastewater treatment plant is, you can tell that we find ourselves in a situation where we have negative removal. And this is not actually strange after I consulted literature to realize that other studies have also discovered that there is negative removal. Rather than you finding phthalates being removed, you find phthalates being increased in the effluent than in the effluent, except for a few of them, like DEP. As a matter of fact, the study by Kumar et al., it was actually stated there, it was a review article where it was stated that there are negative removal of up to 5,700%. So this is not strange. Okay, also to check to see the ecological risk for algae, fish, and crustaceans, invertebrates. We're looking at a case whereby if the ecological risk is greater than 10, then we have a very, very high ecological risk, which means it can actually cause negative effects on these aquatic organisms. If it's between 1 and 10, it's still high ecological risk. And then what we have that is really safe is if they are less than 1. Let's start from less than 1, then we know that we are getting to a safe zone. So for all of them, we see that the risk quotient is really high, except for diethyl phthalates, where the risk quotient is less than 1. So in conclusion, we see that in these wastewater treatment plants, we have a case where there are high effluents of phthalates that have been released on a monthly basis. This study has also showed that the treatment plants exhibit negative removal, and we've demonstrated that from literature that this is not a strange occurrence. It has actually been reported because phthalates is an emerging contaminant which wastewater treatment plants are finding very difficult to remove. And then the estimations of the ecological risk, as indicated, needs to be checked as well because they are capable of causing harm to aquatic organisms. Recommendations: we need an upgrade of the wastewater treatment plants. And when we say an upgrade, we're not just talking about maintenance. We're talking about something that can be competitive as accommodating a wide range of emerging contaminants. And then the receiving water bodies, especially residents who use these water bodies, they really need to be educated to be sure that we are covering this not just from one direction of the end users. And then regulatory authorities as well need to be alerted about this as soon as this study is done. It's an ongoing study. They will definitely be informed of the status of this water. And then the receiving water bodies as well need to be monitored, not just for phthalates, but for other endocrine disrupting chemicals or emerging contaminants, as you may call it. These are some of the references that I consulted throughout this study, and I really want to appreciate you for listening. I also want to thank my supervisor, he's hiding at the back there, for his support, and the University of Venda in general. Thank you.
Okay, the next presentation is on impact of intensive cost groundwater exploitation by Professor Jian Lee. Welcome.
Ladies and gentlemen, good afternoon. Thanks so much for attending the presentation today. I'm Li Xian from Hefei University of Technology in China. My presentation concerns about the impacts of intensive cost groundwater exploitation in North China. My talk sorry. This is not work. Okay. This is not work. No. The PowerPoint can work. My talk will be in 4 parts: background, 2 case studies, and the conclusion. Let's move to the first part. Karst landscape formed by the dissolution of soluble rocks captivate with their unique scenery, creating iconic natural wonders like China's Guilin Mountain. Karst rocks cover a global area of 22 million square kilometers, making up roughly 15% of the land mass, supplying water for a quarter of the world's population. In China, about 33% of the Earth's surface is karst. Karst water resources play a significant role in the supply of drinking water, agriculture irrigation, industry production, and ecosystem maintenance. The large-scale exploitation of karst water resources had led to a series of geological issues, including the continuous decline of water level, spring water drying up, deterioration of water quality, and karst collapse. The study object is to investigate the impacts of intensive exploitation on karst groundwater through 2 case studies in North China, Jingci Spring, and the Xiangshan karst region, highlighting quantitative depletion and qualitative degradation of karst groundwater. The first case study is about Jingci Spring, the most famous karst spring in China. Here we present a geologic map of Jingci Spring Basin. The karst groundwater flow from the north to the south. In the southeast, a part of the groundwater flow encounters the quaternary clay and discharge through fractures as overflow springs. Since the 1980s, groundwater has been consumed for coal mining purposes and groundwater withdrawals. In April 1994, Jingci Spring had been dried up since, which emphasized the need to proper planning to allow the spring flow to return. First, we should investigate why the spring dried up. The primary causes of the decline of groundwater levels in Jingci Spring Basin were reduced recharge from precipitation and river seepage, and increased discharge from mining drainage, groundwater withdrawals, and lateral flow to the quaternary aquifer. Then we built an artificial neural network models for the relationship between the groundwater levels and its factors. This model presented a good performance. The relative contribution of each influential factors were calculated by Garson's formula with the connection weights in this model. From this table, it can be seen that the last year's groundwater level is the most important factor, and coal mining drainage is the second most important factor, followed by precipitation and groundwater withdrawals. Sensitive ranges were proposed to understand how these factors influence groundwater levels. Coal mining drainage and groundwater withdrawal play the most important role of all the anthropogenic factors. Once 2 actions drop below the threshold, there will be an observable effect on the groundwater level. The 2 figures depict the sensitive range of the recharge factors, and precipitation also plays a significant role in the increase in groundwater levels. Based on the sensitive ranges, 4 management scenarios were proposed to predict the groundwater levels. The figures in this slide compared the prediction result under 4 scenarios in the normal precipitation condition and above normal precipitation condition. In the normal years, the spring will reflow only under the 4 scenarios after the year of 2025. This confirms the 4 scenarios as the optimum management strategy. The government began to implement the Jingci Spring Reflowing Project in the year of 2014. The measures included shutting down nearby 200 coal mines and 2,000 enterprises and carrying out water resource replacement project. Thanks to this effort, there was exciting news in this year. The improved water management bring the old spring back to life in January 2025, and this time was very close to our predicted result. The other case study is about Xiangshan karst region in Huaibei City. The karst area is composed of exposed karst area, shallow buried area, and deep buried area. The karst groundwater flows from the north to the south. Karst water is the primary water resource for domestic supply. From the 1990s, with the increase in exploitation of karst water, the groundwater levels had been continuously lowered, and the total dissolved solids concentration had been gradually increased. This phenomenon raises three key questions. Was there a strong correlation between groundwater levels and the total dissolved solids concentration? What were the dominant factors of rising TDS? How did these factors influence TDS increases? We will address these questions in the following section. From the contour maps, there was a significant decline of the karst groundwater levels and a significant increase of TDS concentration in the latter period. So there may be some special consistency between the two variables. The special distribution of correlations between karst groundwater levels and the TDS concentration in this figure exhibit three distinct special patterns: an inverse moderate correlation in the central region, a slight correlation in the north region, and the positive moderate correlation in the south area. To decode these patterns, we apply bivariate local Morans indicator analysis to identify the clusters types. The clusters associated with low groundwater levels and high TDS values were the most prevalent and located in the center area. The cluster with the high karst water level and high TDS values exist in the south. And there were small clusters of high groundwater levels and low TDS values appeared in the north area. We further identified the major controlling factors that affecting the variation of the karst water hydrochemistry. In both diagrams, the dominant cations and the anions were calcium ice and bicarbonate ice. In this slide, different diagrams were prepared to explain the hydrogeochemical processes. Accordingly, it can be seen that most water samples fell in the rock weathering dominant region, and the main mechanism affecting water chemistry is carbonate dissolution. Small samples from the deep buried area fell in the evaporative concentration dominated region. Factor analyses were also executed to determine the controlling factors. Three factors were identified. Factor 1 suggested the most important effect of carbonate dissolution. The second factor indicates the effect of evaporative concentration process. And the third factor indicates the effect of intensive exploitation. From the factors loading scatter plot of samples, we can see four clusters. The cluster marked by red ellipse represented the samples from the shallow buried area affected by factor 1 and factor 3. The cluster marked by green ellipse represented the sample from the exposed area affected by factor 1. And the cluster marked by blue ellipse represented part of sample from the deep buried area affected by factor 2. However, the other part of the deep buried area sample fell in the purple ellipse, which may be caused by the dilution of leakage recharge. But this issue requires further investigation and research. Let's move to the section about how did these factors influence TDS increases. First, we calculate the carbonate dissolution rates. The result revealed that the dissolution rates are highest in exposed area, followed by the shallow buried area, and the lowest the deep buried area. Then the laboratory experiment had been conducted to investigate the influence of carbon dioxide, temperature, and the water flow rate on the dissolution of carbonate rocks. The experimental equipment consisted of 3 parts: the supply device, the reaction device, and the collection device. So here in this table, we've got the result from the experiment. The analysis will carry out to identify that carbon dioxide is the most important factor driving carbonate dissolution. Furtherly, we complemented the numerical modeling to investigate the geochemical reaction occurring along the 2 flow paths. Looking at the tables, we can see some changes over time. In 1998, the data indicates calcite was precipitating while dolomite was dissolving along the flow path 1. Along the second flow path, both minerals were precipitating, but then in 2002, both the values of calcite and dolomite mass transfer were positive, indicating the dissolution of calcite and dolomite. This suggested that the intensive groundwater exploitation lead to intensive rock-rock interaction. Now turning to the figure, these figures, and on the right, the maps of the variation of redox potential helps us to distinguish the reducing and oxidizing condition, that the imposed area was remained consistently oxidizing condition, while the shallow buried area showed fluctuation between weakly reducing and oxidizing condition. And the deep buried area was present as reducing condition. Significant after 2001, increase in exploitation in this shallow zone caused the cast water levels to drop. This transformed the local environment from weakly reducing to oxidizing. In other words, the closed system changes to the open system. There was more oxygen, promoting more microbial activity to release more carbon dioxide, strengthened the carbonate dissolution. Of course, our finding here will need to be confirmed by the follow-up studies focused on biogeochemical processes. Let's summarize briefly. These 2 case studies demonstrate that intensive exploitation induces hydrological geochemical feedbacks and requires management frameworks for karst aquifer preservation. Future research on hydrogeology and biogeochemical responses will guide adaptive strategies. That's all for my presentation. Thanks for your attention.
Thank you so much, Professor Lee, and all the presenters. Once again, we announce that if we have Dr. Palinicherry here, okay, please come forward.
Good afternoon, everyone. First of all, I thank the organizers for having given me an opportunity to share my experience in the field of wastewater. Okay. Today I'm going to share my experience in the topic like sustainable water recovery from chromium-laden electroplating effluent using a multi-channel baffle electrocoagulation reactor experimental studies. If you see in India, we have more than 3 lakhs small-scale industry or electroplating industry effluents are there. And particularly in our region, if you see, we have more around 1,200 number. They are producing large metal-rich effluents in our region and mainly 400 units in Coimbatore itself. So because of that, they release a lot of chromium, mainly you know that chromium and nickel and zinc, they're all very toxic in nature. So they discharge huge amount of wastewater into ground and the surface water resources, they are being polluted. But if you see the current conventional methods, if you see they use ion exchange, solvent extraction, reverse osmosis, acid reduction, chemical hydroxide, but they are very costly and energy intensive. So just we thought of having this electrocoagulation, which takes the advantage of adsorption, coagulation, and filtration. So in this one, we are working on a project with a real-time effluent in the industry. Just we are presenting the results here. And this is a small-scale industry in our place, and they are making like pin coating. Even from that, we have 500 ppm of chromium that is being released into the wastewater, like water bodies. And major things, if you see, there are 3 major processes coming out, wastewater coming out from 3 major processes. One is the acid waste and alkali waste and chromium, which is having only 2 pH. If you see the acidic waste, it is 0.1 pH. And if you see alkali waste, it is 12 pH. So we have these 3 wide range of wastewater coming out of that industry. But if you see all these small-scale industries, they don't have facility to treat the water, so they just that is discharged into the water bodies. And many of the wetlands, 18 wetlands, small wetlands are in our region. They're highly polluted, soil is contaminated. So we thought of working on this problem to remove this chromium and recover water from this one. So initially we thought of, this is a schematic diagram overall, that is hybrid electrocoagulation and adsorption. Just before going further, just I'll say what is electrocoagulation. This is mainly for suspended solids, not for dissolved solids, settleable solids. Suspended solids, you know, we have charges and always it will be in suspension. So when we add some coagulant, normally chemical coagulant, if we add, the particles come together by electrostatic force of attraction and they, they form flux and settle down due to density. But here, we are adding more chemicals. So it will add more tedious to the effluent. So here in electrocoagulation, we add electrodes, we apply potential. So when we add positive potential, metal ions are being released, and the electrons pass, they come through the circuit to reach the cathode, water gets dissociated, and OH and the metal ion they come together, and they form flux, and again adsorption takes place, they remove the chromium. So we can remove 100% actually through this process. So this tedious is a major problem. We all know that more than 3,000, 4,000 ppm in electroplating effluent. So we are working on electroadsorption, but in this study we are talking only about the electrocoagulation. So this is the main objective, that is to establish and evaluate the high-performance integrated multi-channel baffle type electrocoagulation technology for recovery of water. So before starting the experiments, we thought that why can't we use carbon to increase the pH, because electrocoagulation will work under neutral pH. So we thought of increasing the pH. So we conducted adsorption experiment using different types of carbon. We identified 200 micrometer works better. Then these are some of the experimental results we got by adding, that is by allowing the effluent to pass through the carbon first. So 83% we got the removal just with 5 grams. These are batch studies we conducted in the lab. And the pH was actually changed, and also TDS. And then for alkali waste separately we did it, but the chromium removal was very less, and we conducted for 2 days continuously. And then we thought that why can't we add that is activated carbon in the reactor itself, because it will take the advantage of adsorption coagulation in the reactor itself. So you see the initial pH is 2. It's a combined waste, not acidic, alkali. It's a combined waste. So we applied a current and minimum reaction time and the RPM, and then you can see the chromium level varies from 300 to 500 ppm. It is very high. You all know that. Then, so with the iron plus activated carbon, with the aluminum electrode with activated carbon, aluminum alone and iron will try. And iron and activated carbon performed better. But one disadvantage we saw that we are adding carbon into it extra. So along the sludge, carbon will be deposited. So we thought that why can't we go further? So we did some SEM analysis also for this activated carbon. So from this we can find out macropores, and the deposition also in that one you can see the third one after saturation point. So the salts got deposited, and when we analyzed, the chromium salts are also there, and this is confirmed by EDOX again. This is the original left side. You can see the original one, 77% carbon. And when we go for the analysis, after the treatment, we can see even the nickel and chromium and a small portion of zinc is also there. And we tested the salt that is deposited on that also. And XRD results also confirm the same thing. We have the traces of chromium, nickel. So activated carbon worked very well. And HPLC also analyzed. We gave that water. And the peaks before the treatment were removed after the treatment. So it confirmed the removal of organic contaminants from that. Then FTR analysis, all these results confirmed the best results. But one thing, as I told you, when carbon settles along with the sludge, again it creates problems. So we thought of going for the continuous flow reactor. So multi-channel baffle type, we started working. So instead of batch studies, we allowed the water to pass through 50 ml, 100 ml, 500 ml per minute. And at 550 ml, it performed better. For the 500 ml, no, the removal efficiency was low with the same pH. It is in the laboratory studies. And again, we tested the sludge. Sludge, you know that it is amorphous agglomeration form. Metal hydroxides are formed and adsorbs the metal ions. And we tried with 3 electrodes, aluminum, iron, and titanium. Because titanium electrode we developed in our lab. And for dye, it worked better. But for heavy metal removal, the efficiency was less because of the surface chemistry. And we tried with aluminum. You can see on the left side, only chromium, less amount of chromium was removed when used aluminum. But when we tried with titanium dioxide, better. But for this one, dye removal, this titanium coated aluminum performed better. And the third one, you can see iron. Even you can see chromium and zinc. All the heavy metals were removed because of the surface chemistry again. So we thought of working with iron. So this diffraction peaks confirmed the removal of chromium and chromium and nickel using iron electrode. So finally, we started working in the laboratory, in the industry. We kept this multi-channel baffle type in the industry itself. You all know that there are 6 parameters which control the efficiency. One is number of electrodes. If you have more number of electrodes, we'll apply more current, more metal ions will be dissolution, and more removal of chromium. Second one, inter-electrodation. We have to keep the electrodes very nearer so that the particles will interact with each other, hydroxides will be formed, and the deposition will be there. Third one, inflow rate. If the flow is higher, we have to have more electrodes. And then current density, same thing. If you apply more current, more efficiency, but if we cannot, we cannot go beyond the limit because electroflotation will occur. Instead of electrocoagulation, the froth will be at the top. Then reaction time. We have to find out the optimum time, finally settling rate. So we conducted different experiments, 5-pair system, 6-pair system, and the gap, inter-electrode distance. Finally, we optimized it. You can see we varied the different pH because every day the industry effluent, the characteristics will be changing. We cannot have a fixed one. So we tried 1 month being in the industry, and we tried that. And finally, the one side we have to add alkali because pH will be going down after some time in the electrocoagulation reactor. So finally, we found out the optimum pH for the electrocoagulation, that is reactor is 2.6, so that we can remove 500 ppm of chromium. Then, okay, we remove the chromium, the sludge comes down. Again, like chemical sludge, what we are going to do? We thought of recovering iron. So along this, that is to the sludge, we added electroplating effluent again, the acid waste. Chromium effluent we are treated, but still acid effluent and alkali effluent there. So we added acid effluent, so you can see we can recover iron oxide. You can see there. That is a magnetic pellet. The sludge is being converted into the iron oxide. We can recover, but chromium 6 is converted to chromium 3, so it is non-toxic. We can, again, we can recover chromium from that. So it is a zero liquid discharge like that we can have. So just finally I'll show you the configuration. 3 configurations we tried. One is hopper type, second one baffle type, third one upflow reactor. This is like hollow, there is a hopper type where we have recovered the iron. So you can see the iron being deposited at the bottom, the sludge is being converted into iron oxide. So the problem of sludge formation is also avoided. So this much we can recover the iron oxide with this one. And this is in the industry. This is multi-channel baffle type reactor, which we have tried in the small scale industry, the field itself. So you can see how much finally the water has been treated. This is the reactor. We have given 1.4, 1.5 hours reaction time, and you used the 10 sets of electrodes, but it's a monopolar. But now we are trying with the dipolar electrodes. So this is another configuration. The last one is upflow. From the bottom, you can see how much removal is there. This one, no, within 10 minutes, we can remove all the 500 ppm. So you can see how much, efficiency. So finally, we got only 5.5 ppm of chromium only when we tested. So 80% water can be recovered. The sludge iron can be recovered. It can be converted into chromium 3. Now we are working on generation of hydrogen from this one because water will be dissociated. No, we are trying to get this one. So this is the conclusion. 99% of removal of chromium is there. We can recover water, which can be used again for the industry, and iron can be recovered. The operating cost is very minimum, and if you use solar, then we need not say, still it will be reduced. So it is one of the viable, efficient, and cost-effective method. And this is our project team in the industry. Thank you.
So thank you, madam, for your presentation. Now I call upon Professor Vimal Chandra Srivastava to summarize the session.
Thank you so much, Professor Kaveri. So before that, I'd like to announce that we will be having dinner at 6. Before that, we can take the few of the questions if you have. So any questions, if you wish, you can raise the question to us, any of the panelists. Otherwise, we'll be happy to close and we can discuss any queries or otherwise during the tea break or during the dinner time. So I guess it is not much of the questions. We have few audiences from, not only us, a few birds were also here. So it's good to see them. So thank you so much everyone for listening patiently to her, and I thank all my speakers in this session for their elaborative talks, and we have learned quite a few things from each other, and hope to meet you and discuss further. Thank you so much. So we end the session now, and I will be having dinner at 6 in the hall adjacent to this hall. Thank you.